Well, what's up, everybody? Welcome to Earth Science and welcome to Marking Period 4. You've made it through 3/4 of the class. We're getting close. Great job so far. All right, so we've got a new one of these things, a new one of the all MP3 assignments or MP4 assignments. I got to get used to saying that. All MP4 assignments guide, where we will be filling things in down there. But let's talk about what we're going to be doing here. We're going to do two units, tectonics and Earth's history. So I threw a few new pictures up here. 3 of these are mine, and then I stole this one from the internet. And I stole it because I want to say, like, what are we doing here with tectonics? What we're trying to do is figure out, why does the Earth look the way it does? And one of the simplest, shortest ways to say it, which I'm going to say it in a lot longer, more complicated way for like 10 weeks here, but a way that you can like encompass all of geology in one sentence. It's like a famous saying is that the highest mountains in the world are composed of what kind of rock? Do you see these layers right here? And if you did a good job last marking period, then that'll make sense. What kind of rock is that? Those layers, hopefully sedimentary, is triggering in your mind. So how do we have sedimentary rocks that high above sea level? The highest places on Earth are composed of rock that was formed below sea level, sedimentary rock. These are the Dolomites, a mountain range in like northern Italy, part of the Alps. Okay. So what like forces, how tectonically does all of this stuff happen where we get rock that has gone up in elevation that dramatically from below sea level to well above sea level? Rocky Mountain National Park, another like just in the Rockies where we've got, hi, Mr. Davis, where we've got different kinds of then you get into metamorphic and igneous rock in the middle of that larger range. The front range of the Rockies. So, like, this is Red Rocks, which is south of Denver, and this is the Boulder Flatirons, north of Denver. I mean, you can drive from like the Mississippi River and drive, getting closer and closer and closer to the Rockies, and you won't see anything that's like not just flat corn and wheat fields for a long time, days, and then all of a sudden you get there and boom, these things like just come sticking straight out of the ground. Here's just Google image a bunch of them. They're impressive. They're huge. And consider that at the elevation of Boulder, you're already about a mile above sea level, maybe a tiny bit below. By the time you get all the way up there, we're talking a pretty serious thing for a sedimentary rock that, again, formed below water to get that high. So that's the theme. And then the Earth's history part, we're going to have to like think about all of the things we've done in Earth science and use that to put together like a whole version of the whole planet's history. So, with that said, we'll do the usual. We'll do some notes on tectonics. Big scary 13-page note packet, but don't panic for now. We'll do the same thing. Like we'll do a couple pages at a time, and when the YouTube video stops, you're good, and then we'll pick back up with it in the next lesson. So, a good place to start is how does the outside, or let's go outer shell. How does the outer shell of our planet behave? All right, it's like scary thin. This thing that we consider so massive and so big. I mean, we're such tiny critters on a pretty large planet that if you cut an apple in half and look at it from the side, the proportion of like the thickness of that skin to the size of the apple, it's about right for the proportion of the thinness of our outer shell to the whole entire planet, which is a little alarming because it's violent and scary down there. All right, and it can make pretty big messes. If you saw the news at all last week, and granted the news is so saturated now, but there were some pretty good volcanoes, or one going down in the Caribbean, and we'll bring that up. We'll talk about it. All right, so where are we going? This guy is actually the top of an Earth Science reference table. I deleted it off the bottom, and we're not going to get into the nitty gritty too bad today. We're just going to use it to say, okay, here they are, and always available to you because it is a reference table. Here they are, the layers of the Earth: inner core, outer core, stiffer mantle, plastic mantle, rigid mantle, crust. So that's a mouthful, right? Go like core. Okay, that makes sense. We know the core is way down there. Then what is this mantle thing, and why do we have it subdivided into 3 different pieces? And what is the crust? So let's break this down. Now, what I want to do, I don't think this diagram does a very good job of what goes on at the top. So, and they should like do one of these things. You ever seen a diagram where they do a little box and then it says like zoom? We'll make it bigger. So we're going to make the outside of the diagram larger in this diagram so that we can see like a little bit better what's going on. So at the very top, I just have like outside of the Earth. So I have what we've already learned about, which is the atmosphere. And that's it. We're going to leave that alone. Below that, we've got the thing that we live on, which is called the crust. All right. Below that, we've got this thing that's called the rigid mantle. So it may feel like I'm not giving you anything new. Yes, that's all available right there. But let's really think about what these mean and what the next thing down means. The next thing down is the plastic mantle. MANTLE. So this is a good definition, and we don't really have to worry about the atmosphere, right? For these three, this is a good definition of these layers that definitely exist that we've identified in like a chemical sense and like a sense of like what the stuff is that makes up these layers. But we can think about it in a different way, and that's important and valuable in tectonics. We can think about it in terms of their behavior, how they like act. And in that sense, these two behave the same. The crust and rigid mantle like physically act as like they're stuck to each other. They behave the same as all these tectonics things happen that we're gonna study. Those two are like one thing essentially in terms of how they behave. And I know behave, like don't think of like human behavior. Their natural way of functioning. So together we call those two the lithosphere. Lithosphere. And again, that is on the reference tables, but like what is this? So why am I getting picky about this? Is that how do these two actually function? Is that they're rigid. That's the best term to use. Another one that's used in geology is brittle. If they have to deform, if enough pressure is put on them where something's going to happen, like if I take this beaker here and drop it on the ground, when it hits the ground, there's going to be enough pressure on that glass that something's going to happen. It's going to deform. It's going to break because glass is brittle. It's going to smash into pieces. Similarly, this chunk of lithosphere, the crust and rigid mantle together, if put under pressure, will break, will snap, will crack. And if you know what's going on with like earthquakes, there's a sneak preview where we're going this unit, right? So it breaks, cracks. I mean, there's other ways you could probably say it. Brittle is definitely the real geology term. It undergoes brittle deformation. Versus down here, and this is we didn't draw the whole thing, so it's like this and then down, down, down. Is behaviorally the next layer down was called the astenosphere, ASTHENO sphere. The term plastic in the world of geology or material science in general is going to mean that there is a flow, that when pressure is put on it, it doesn't crack, it bends. We are still saying solid here. So this is more about a solid that flows. And the real geological term for that is plastic deformation. I know when you think plastic, you think of like, plastic cup or whatever, right? But the plastic is a term for that, for flowing under pressure. Now it is, and this is where earth science oversimplifies. If you're just taking the regions, this answer is going to be correct. If you go and want to become a real geologist, let's have a conversation about how this is a drastic oversimplification. But what the Regions likes to ask is, why does this lithosphere move? It's going to be on the lab that you're going to do first. Why is this lithosphere moving? Like you're moving right now on this tectonic plates at about the speed that your fingernail grows. Not very fast, but why does it move? Why does lithosphere move? The real answer is that it's complicated. There's a lot more going on than this. The simple New York State 10th grade earth science answer is because of convection in the astenosphere, which sometimes is also called upper mantle. Does your reference table say that? Doesn't really say that. So they'll stick to astenosphere. Convection in the astenosphere is why this moves in an oversimplified sense. Okay. Um, so yeah. Now again, earthquakes, volcanoes, things like that are a function of this behavior thing. So chemically, we can say that there's a crust, there's a rigid mantle, there's a plastic mantle. Behaviorally, there's a chunk that cracks and there's a chunk that flows, and that cracking is going to be down the road. Why we end up talking about earth science. I'm sorry, why we talk about earthquakes. Let's throw in one more thing here. There's an important right between the black and the white there, which is the crust and the rigid mantle. So I'll swap to purple. Between the crust and the mantle, which means I'm going to have to go right through my drawing here, is a line, not a layer, just a line that separates, called the MOHO, which is short for the Mohorovich discontinuity. That's the dude that discovered this. That's the line that separates essentially crust from mantle. So you can consider chemically everything below the MOHO as mantle, everything above it as crust. But then again, behaviorally, which is more important for tectonics, lithosphere, asthenosphere. And of course, this is ignoring the core. We're not worried about that because we're talking like near surface stuff that's going on. We'll worry about the core another time. Okay. So to push us forward to what you're going to be doing in the lab, Earth's rigid outer shell is broken into large pieces called tectonic plates. Or another way to say it, I'm going to make this a little bigger. Lithospheric plates. Occasionally, you're going to see them referred to as crustal plates. And I don't want you saying that in a lab. This is dead up wrong. So why do you think Mr. F does not like this term? Maybe I'm not going to skip that. Maybe I'll come back to it. I don't know. But think about that. Why do I not like this term considering what we just set up here? Tectonic plates, lithospheric plates. Okay, so our final job this week and what you'll do in the lab that begins momentarily is to figure out how this all leads to earthquakes and volcanoes. All right, so here's a map from your reference table that I don't think I'm going to go into detail too hard on because you need it in the lab. But that is available right in your reference tables if you want to make a note of which page. Page 5. All right, and it's got all the stuff that we need. Again, I'm not going to make a big deal out of this right now. You're going to figure out where volcanoes and earthquakes take place in that lab. So what do I need to get out of today? Blank, the rigid outer layer of the Earth. What do you think? Lithosphere, which contains the crust and rigid upper mantle. And TLE. Softer liquid layer. No, not layer. It's not a liquid at all. Softer solid layer. That's why I said that there. Asthenosphere. Which flows. And now the premise of the lab, and again, I didn't get into this here, what you'll be doing in a few minutes, is that earthquakes and volcanoes tend to cluster at these plate boundaries. This is where the action is. You've probably heard of San Andreas because two enormous pieces of rock, I mean, a piece of rock that like underlies most of the Pacific Ocean, and a piece of rock that's the size of our whole country plus half the Atlantic Ocean and Canada, are grinding against each other. Those are two heavy things. When that happens and they slide, there's going to be earthquakes. So these earthquakes and volcanoes tend to occur near plate boundaries. Except once in a while we get these weirdos. The weirdos are called hotspots. Like Hawaii, there's no, like, according to that simple idea that they're near plate boundaries, there's no plate boundaries anywhere near Hawaii. So why is there an active volcano there? And here, and here, and here. That's because those are these things that we'll unpack in better detail later, called hotspots. All right. What do you think? Good start. We'll do Earth cuts later. That's a good overview on just the outside of the Earth. It's broken into these chunks that are moving around. Now we got some names for some of those chunks, and we'll use that and push ourselves forward, and you will do great. Thanks for listening. Welcome to American Period 4, and good luck on the lab you're about to start.